With the basic tools of trigonometry at hand, we can finally study vectors. And in this video, we're going to see primarily three things. We're going to look at vector definition, scalar multiplication, and vector addition. Let's start with the definition. A vector is a quantity that possesses both a magnitude, that is a length, and a direction. We normally denote a vector by an arrow whose length represents the magnitude, the size of the vector, and whose direction is given by the orientation of the arrow. We also generally denote the vector by a bold capital letter, or sometimes by a letter with an arrow on top. Examples of vectors from physics are displacement, velocity, acceleration, force, and many more. So what can we say about vectors? First of all, any two vectors are equal if and only if both their magnitudes and their directions are equal. For instance, in this case, the vector A and the vector B are equal to one another because they have the same length and the same direction. However, the vectors in this picture are not equal because even though A and B still have the same magnitude, B points in a different direction. To understand this conceptually, you can think of A and B as displacements. If you move along A and you move along B, you moved the same distance in both instances, but the end point will be different. So what can we do with vectors? First of all, we can move vectors on the plane at any location as long as the vector is not stretched or compressed, and as long as its direction is unchanged, the vector will be the same regardless of where it is drawn on the plane. So all the vectors in this image, for instance, are equal to one another. More interestingly, we can do scalar multiplication. What is scalar multiplication? First of all, let's define a scalar. A scalar in physics is a quantity that only has a magnitude. That is, it's a quantity that it can be expressed only by a real number. It doesn't have a direction. One example of a scalar from physics will be time. Another example will be mass. So, to be precise, let's say that we have a certain scalar, we call it c, and the scalar has the value 2. What is the effect of doing c times a? In this case, of doing 2 times a. Let's address this graphically. If we think of a as a displacement, that means that we start at the tail of a and we move along a until we get to the tip. That means that we have traveled a length that is equal to the magnitude of a. Therefore, we can say that 2 times a can be achieved by drawing another vector and connecting it head to tail to the first one and moving along the first vector a and the second vector a. That is twice the vector, and it therefore results in another vector which we can call b. B will be the product of a scalar, in this case 2, multiplying the vector. So we can see from this, the scalar multiplication is the multiplication of a vector by a number which gives us another vector. The direction of the resulting vector in this case doesn't change because the scalar is a positive number. The only effect of the scalar is, in this case, to stretch the vector and increase its magnitude by a factor of 2. What if c is negative? Let's take, for example, the simplest case, -1. What is the effect of multiplying -1 by a? Well, we know, first of all, that multiplying a number by 1 cannot change its value. Therefore, the 1 cannot change the magnitude of a, that is, it cannot stretch it nor compress it. But what is the effect of the -1? Well, once again, if we think of the length of a as a displacement, moving along a from its tail to its head is a positive displacement. And by definition, the negative a, which is -1 times a, is a vector that has the same length as a, but points in the opposite direction. The other thing that we can do with vectors is vector addition. Namely, we can add two or more vectors. Let's again take the simplest case of adding two vectors and see how this works. If we want to add A and B, as in the image here, if we again think of this in terms of displacement, A plus B will correspond to moving along A first and then moving along B, and then seeing where we end up. Graphically, we can do this by joining the two vectors, by joining the tail of B to the head of A, and therefore we see that this is equivalent to starting at the tail of A and ending up at the head of B. This is in itself a displacement that we can describe by another vector. We call this vector C, and this vector is the sum of the two vectors A plus B. Now the question that arises here is, does the order in which we add the two vectors matter? Namely, if I want to add B plus A, does that make a difference, or do I get the same answer? We can answer this question again graphically. We switch the two vectors. We start at B, we move along B first, and then we join A to B and move along A. The net result in this case is once again the sum of the two vectors, B plus A, which again we call C. But because we call the vector the same name, this seems to imply that the sum is the same. We can prove that the sum is the same by using what is known as the Parallelogram Rule. We can slide the vectors B and A onto their opposite sides so as to form a parallelogram, therefore the name Parallelogram Rules, and we can see that the two sums are equivalent to one another. That is, moving along A and then along B gives the same vector as moving along B first and then along A. And so we can conclude that the sum of the two vectors A plus B is the same as the sum with the two terms reversed. Mathematically, this means that the addition is commutative. So we can conclude that vector addition, just like number addition, is commutative. What happens if we want to subtract two vectors? Let's say we want to do A minus B. How can we achieve this? Well, first of all, we know that minus B can be thought of as negative 1 times B. And therefore, we can think of A minus B as A plus negative 1 times B. But now we know that multiplying a vector by negative 1 is the same as flipping the direction of that vector. So, in order to calculate A minus B, we first calculate minus B, then we join minus B to A, and once again draw the vector that goes from the tail of A to the head of B, and that will be our resultant vector, which we call D. D then corresponds to A plus minus B, which is nothing more than A minus B. Clearly, you should verify that A minus B is not the same as B minus A. That is, subtraction is not commutative, just like it's not commutative with numbers. I'm going to let you verify this little bit here. All of this analysis is useful, but it's still just a graphical analysis. We want to be much more precise. So in the next video, we're going to put together the trigonometry that we learned in the previous videos and your knowledge of algebra to make all of this more systematic and quantitatively precise.